So good morning student. In today's class we will cover our inverter lecture with L load and in my previous lecture as we have completed the R load with the single phase half bridge topology. Now we will see the how is the behavior of voltage source inverter or output voltage or current waveforms in case of L load. So see, this is the circuit topology. What we have do here is we connect a load which is have a value of L between the point A and O, and point O is the neutral point where we have divided our input supply into two parts, that is VDC by 2 and VDC by 2. So this is the switching logic table which is shown in the see in this switching logic table. It is a very important switching logic table as it will be same for all the loads, that is R, L, RL, RLC loads, because what is the property of a voltage source inverter, that the output voltage waveform is independent of type of load. So for the any type of load, output voltage waveform does not change. It is same as the square wave in all the cases. But this switching logic table we will see in the circuit topology. As T1 is on, then V naught is greater than 0, I naught greater than 0, and power greater than 0. See how we assume reference polarity to be plus minus V naught, which is an instantaneous output voltage, and I naught to be instantaneous output current, which is flowing from point A to O, and load is connected between the point A and O. So when T1 is on, or we can say that if the gating pulses are applied for the switch S1 or T1, and then the output voltage appears across the load, which is equals to VDC by 2, and the current is flowing as the reference polarity we will assume from A to O. So I naught is positive, and at the same time V naught is positive because V naught equals to plus VDC by 2. So if you multiply voltage and current, then power is also positive. So if the thyristor is on and power is positive. Next we will see that inductor has a property because it stores the charge. So it will release the energy through the path D1 like this. So this is the how inductor release the energy through the diode D1. So if the diode D1 is on, then we will see that this point V0 the voltage V0 which is positive, because because this plus polarity is connected to supply voltage plus polarity, and negative is connected to supply voltage negative polarity. So in this case the output voltage is again positive, but the current direction is reversed, or we can say that it is opposite to the reference current polarity. So I naught should be less than 0 and V naught should be greater than 0. So if you multiply both, then power should be less than 0, or we can say that power is now delivered, or in the first case power is absorbed by the load. And now we will apply gating pulses for the thyristor T2. If gating pulses are applied for the thyristor T2, then what? See, the current will be flowing like this, because thyristor is a unidirectional device as well as the diode is a unidirectional device. So this polarity will makes diode to be reverse bias, so it is open. And now if the gating pulses are applied for thyristor T2, then current will be flowing opposite to the reference current, but and at the same time voltage should be just negative polarity, because negative is connected to positive now, and plus polarity at the point A is connected to negative of the supply voltage. So in this case when thyristor T2 is on, then voltage should be negative and current should be also negative, because it is opposite to the reference polarity we assume from A to O. So in this case thyristor T2 also power should be greater than 0. And now as soon as we remove the gating pulses for thyristor T2, it is off. So now the inductor is again releasing the energy. So as it releasing the energy, so now through the path diode D2, so current will be flowing through the diode D2 as shown by the arrow polarity. So in diode always current flow from anode to cathode, not from cathode to anode. So current will be flowing like this. So in this case we again see that the reference current is now positive, because it is flowing as the same as the reference current polarity. So now current will be flowing from A to O, VDC by 2, and again diode D2 to load. So reference current so now current will be positive, but voltage is negative, because again the load side point load polarity minus is connected to plus of the supply and plus is connected to minus of the supply in the negative half. So in this case power should be negative. So what we have understand from this table, that in case of thyristors power is positive, that is source will absorb the energy, and in case diode it will just freewheels the energy or through the freewheeling diode path. So in previous lecture we will see that in case of resistive load these diodes are not come into picture, because there because the resistor have a not a and although it is an energy storing element, it dissipates the energy in the form of heat, but in case of inductor it just releases the energy through the freewheeling path. So this switching logic table is very important, because in further lectures we will see RL load, and in full bridge inverter also this logic table is just working same. So we can continue this lecture with the waveform. What is the output voltage waveform across the load? So as we see, as the thyristor is on, then see from 0 to t by 2, 0 to t by 2, this voltage polarity is positive, because output voltage is plus VDC by 2, and in the negative cycle T2 is on, so VDC equal to minus VDC by 2. So it is same as the resistive case, resistive load case in case of half bridge inverter, because I already told that in VSI the output voltage waveform for all the loads remains same, because it does not depend the type of load. And this dash dash waveform which is denoted by the red color pen V01T, it is the instantaneous current waveform of the fundamental voltage. So fundamental voltage, instantaneous voltage waveform, it is a sinusoidal in nature, because for in Fourier series analysis we will see that it is a sinusoidal nature. So now we see what is the output current waveform. So output current waveform in case of the inductive load, see when the inductor, when the current passes through the inductor, or we can say that when the DC excitation is applied to an inductor, then its waveform will be triangular in nature. See, V naught equals to VL, because V naught output voltage equals to voltage across the inductor, which is equals to L di by dt. So I naught dt is equals to VDC by 2, because V naught equals to Vs when the thyristor is on. So if you want to calculate the expression of current, then I naught equals to integration of 1 by L VDC by 2 into dt. If we solve this expression, then we will see that it is a straight line expression. So this straight line expression is shown in the diagram like this, but it is drawn from minus I naught maximum, because because it is just like a steady state waveform. So inductor have an energy of minus I naught maximum in the steady state, so it will be drawn from minus I naught maximum, because inductor is charged up to minus I naught maximum current in the steady state. So this will be drawn from minus I naught maximum to plus I naught maximum. And now we will see that in the voltage waveform 0 to t by 4, or in current waveform 0 to t by 4, here from 0 to t by 4 voltage is positive, which is equals to plus VDC by 2, and current is negative minus I naught maximum. So current is negative, voltage is positive. So see in that switching logic table, voltage positive, current negative. So voltage positive, current negative, that is diode D1. See diode D1, this is the case of diode D1. So diode D1 is conducts from 0 to t by 4. So 0 to t by 4, write D1, and see from t by 4 to t by 2, t by 4 to t by 2, again voltage is positive, but here current is positive. So both voltage and currents are positive. So both voltage and currents are positive. This is the case of thyristor T1. So thyristor T1 is on, thyristor T1, or we can say that the switch S1 is conducts from 0 to t by 4 to t by 2. So we write the S1 to be in between the t by 4 and t by 2, and again continue. So again after pi we will see that voltage is negative and current is current is positive. Voltage negative, current positive. So voltage negative, current positive. This is the case of D2. So we write the D2 in this duration of pi to or we can say the t by 2 to 3t by 4, and after 3t by 4 to t switch S2 is conduct, because voltage is positive and current is also positive. So in this way we will mark the switching device conduction sequence by seeing the switching logic table. So in this way the devices are conducting and output voltage obtained to be square wave. So this is the AC one. Now we will see the fundamental thyristor current, or we can say that the fundamental nahi, because IT1, this is the current through the switch S1 or thyristor T1. So if we will want to draw this IT1, so see that it from 0 to T by 4 diode D1 is conducting, so there is no conduction through the diode, so we mark it as G. So we will see that no current is flowing through the thyristor T1, so we will draw on the x-axis like 0. And from T by 4 to T by 2, as the switch S1 or thyristor T1 is conducting, so we will draw the waveform to be part of this from T by 4 to T by 2 as shown above in the output current waveform. So output current waveform is just same as the thyristor current waveform. So we will draw this section of waveform from T by 4 to T by 2 similar like this, and from T by 4 to T by 4 to T by 2 to 3T by 4, again current is 0 because diode D2 is conducting, and after 3T by 4 to T, thyristor T2 or switch S2 is conduct. So we will draw this negative part of the waveform from T by 2 to 3T by 4 to T like this. So this is the switch current waveform we will draw. And this red color mark waveform is I01 maximum. This is the fundamental waveform which is sinusoidal in nature. So we will draw a part of waveform like this, because in this part only thyristor current is flowing, so we will draw up to a T by 2 like sinusoidal fashion. What is the diode current waveform? So diode current waveform will be just I note output current waveform, because where the diodes are conducting we will take the parts of the waveform from the output current waveform, and we will draw similar as we will draw for the thyristor, but where the thyristors are conducting, diodes are not conducting. So this is the case, and we will draw again fundamental component waveform in the sinusoidal fashion. So what will we see from the waveform is that it lags, current waveform is just lags by pi by 2 than the voltage waveform, because it is a pure inductive load, so current will be lagging the voltage by exact 90 degree. But in my next lecture we will see in case of RL load it will be lagging at angle of phi, because here combined RL effect is there, so it will be exponential in nature, and as well as the phi angle through which a current is lagging through the voltage waveform. So in this waveform, conduction time, each diode is conducting up to T by 4. See, each diode is conducting up to T by 4. From 0 to T by 4 diode D1 is conducting, and similar from T by 2 to 3 T by 4, that is T by 4 duration diode, each diode is conducting. So we will write conduction time, each diode is conduct for T by 4, and each thyristor conducts also for T by 4, because it is just a symmetricity. And for the both diode and thyristor, then add up both T by 4 and T by 4. So both, if we question, it is asked that both thyristor and diode case, so add this and it is conducting from up to T by 2 duration. So what is the output RMS voltage across the load? So output RMS voltage is same as the previous case. In case of resistive load, it is equals to VDC by 2, because voltage waveform is just like the same. And what is the conduction angle of each thyristor and each diode, which is equals to T by 4, or T by 4 equals to pi by 2. So this is the conduction time of the thyristor or diode. But if we see in the duration of 180 degree, so from 0 to pi, both thyristor from 0 to pi, and then we will see that each diode and thyristor conducting up for a diode conduction equals to thyristor conduction equals to pi for total of 2 pi duration, or we can say that total of t time duration. Both the thyristors and diode are conducting for up to a 180 degree duration. Next point number 4, we want to find now thyristor average current or thyristor RMS current. So thyristor, it is just like a switch, so we will draw the part of this waveform from IT. So IT, it is a just like a triangular waveform. So if we will want to find the average value, then what we will do, we just take the area under the curve of this waveform. So it is equals to 1 by 2 base into height divided by total time period t. So in this way we will calculate the average value. It is the area under the curve of this small triangle from t by 4 to t by 2. and it is same like the diode current average value, because in diode current it is the same conduction of T by 4. So this value is same for the diode case also. And now we will find the RMS value of this thyristor current waveform. So how we can find the RMS value of this total total switch current waveform? So as we all know, by shifting property, the RMS value will not change. So what we'll do, we will shift this waveform from T by 4 to 0. So if we shift from T by 4 to 0, then it will drawn from 0 to T by 4 like this. So we want to find the RMS value. Then what we'll do, first of all we write the expression of this straight line. So it is just like a y equals to mx plus c form, y equals to mx, only y equals to mx form. So slope of this straight line is equals to y upon x. So I naught maximum divided by pi by 2, which is the slope of this straight line, and multiply by theta, because on the x-axis it is a omega t, which is equals to just theta. So into theta. So if we will take this expression and find the RMS value of current, then we will apply 1 upon 2 pi from 0 to pi by 2. From 0 to pi by 2, what is the value of current? It is 2 I naught max divided by pi into theta whole square d theta whole raised to power 1 by 2, because we want to find the RMS value. So the RMS value for thyristor as well as diode case is same, because of same conduction of thyristor and diode. Now we will find that the fundamental thyristor currents RMS and average value. So in R load we will see that which is the case of half wave rectifier. So we will directly write IT average equals to Im by pi. But here we will see that it is just like a half wave rectifier waveform. So it is just a half portion of this half wave rectifier output current waveform. So in this case, see, if we want to find, then we will write first of all the expression of current. So IT01 means fundamental current. So it is equals to I01 maximum sine omega naught t minus 90. Why minus 90? Because it is shifted up to 90 degree or start from 90 degree. So this is the expression of current. So again apply integration 1 upon 2 pi from 90 to 180 degree I01 max sine omega naught t minus 90 degree. So in this way, we'll calculate this expression by putting the upper and lower limits. Then it is equals to I01 maximum divided by 2 pi. So what we will see from this expression is that this is the just half the value of half wave in case of R load. So in R load, we will calculate it to be a I01 maximum divided by pi, but here I01 maximum divided by 2 pi, because it is a half the waveform. Because here the full waveform is showing from sinusoidal nature up to pi, but here a half section of the waveform is we will take. So it will be equals to I01 maximum divided by 2 pi. And if we want to find the RMS value of the thyristor current waveform, then how we will calculate the RMS value? See, this is the trick we will apply for the calculation of RMS current waveform. So we take two waveform from 0 to 90 degree, that is I01 maximum, and from 90 to 180 degree I01 maximum, because we will take this half wave rectifier output waveform from 0 to 180 degree and break this waveform into two parts up to from 0 to 90 degree and 90 to 180 degree. And due to same duration from 0 to 90 and 90 to 180, we will say that RMS value of this first waveform is I1 and second waveform is again I1. And we will know for the half wave rectifier case, RMS output value is equals to Im upon 2 or I01 maximum upon 2. And now we will apply the RMS logic. So total RMS equals to root mean of square of this I1 square and I1 square, which is equals to I01 maximum divided by 2. If we calculate this value of I1 RMS, so I1 RMS means the fundamental RMS current flowing through the switch thyristor T1, or same as the diode, which is equals to I01 maximum divided by 2 root 2. So in this case, this is the expression of switch current fundamental component. So in this way we will calculate the thyristor's average RMS value, and as well as from the fundamental case we will calculate the average as well as RMS value of the thyristor as well as diode current. Now we will write the Fourier series. So Fourier series same as in case of resistive load. summation n equals to 135 to infinite to VDC upon n pi. VDC means supply voltage, sin n omega naught t. So if you want to find current, then simply divide by XL, because our load is inductive, so impedance is XL. So XL equal to n omega L. Put n omega L. So n omega, put the value of this voltage waveform from the upper, and put XL equals to n omega. So it is n square in the denominator, and sin n omega naught t minus pi by 2. Why minus pi by 2? Because it is a pure inductive case. So in this case, current lags exactly 90 degree to the voltage. So this is the Fourier analysis of this air load. Now we will calculate the fundamental displacement factor. So fundamental displacement factor, it is the angle between the fundamental voltage and as well as fundamental current. So in case of resistive load, it phi 1 equals to 0. Now in case it is a 90 degree, because pure inductive load, so voltage and current waveforms are shifted by 90 degree, or phase displaced by 90 degree. So FDF equals to cos 90 degree, which is equals to 0. And now we will calculate the fundamental power output across the load, which is equals to V0 on RMS, I0 on RMS into cos phi 1, and which is equals to 0, because cos phi 1 equals to 0. So this overall term is equals to 0, and P01 equals to 0 watt. So what we will conclude from this? So there is no real power. So as we all know, for inductor is never consumes the real power, so it is equals to 0. And Q01, which is the reactive power of output due to fundamental component, which is equals to V0 on RMS, I0 on RMS, sin phi 1. So if you put the value of phi 1 equals to 90 degree, then it is V0 on RMS into I0 on RMS. So consumes reactive power. So inductor consumes the reactive power. This expression is showing. Now we will calculate the maximum or peak inductor current. So this is the inductor current waveform, which is start from I0 maximum to I01 maximum, from negative to positive side up to T by 2. So if you want to calculate the peak inductor current or maximum load current, because we will see that the load is actually an inductive load, so we will calculate maximum or peak current through the inductor as well as load. So VL equals to VDC by 2. So VL equals to VDC by 2, which is equals to LDI by dt, which is the output voltage across the load, LDI by dt. So what is the change in the current? It is minus I naught maximum to plus I naught maximum. So if we calculate the difference of these two, then it is 2 I naught maximum. For up to what time? 0 to T by 2. So divide by T by 2. So by this expression we will calculate the I01 maximum. So this is the peak inductor current or maximum load current, which is VDC into T divided by 8L. So in this way we will done all the calculation regarding this half wave topology of voltage source inverter, in which first of all we will see the circuit topology, and we will see the switching logic table, and through which we will draw the waveforms. So in this way we will complete this lecture in the inductive load case. In my early next lectures we will see this half bridge topology in case of RL load. So thank you.